Assalamu alaikum. I think we'll start the session. My name is Ali Rada Hussein. I will be chairing with my colleague, Engineer Hamad Al-Hatmi, this session, inshallah. And we apologize that we have only 3 speakers today. It's supposed to be 5, but two of them, I think they didn't arrive at all. So hopefully it will be a short session. The first speaker will be Dr. Leo. Dr. Leo is a senior scientist from QEERI. QEERI is the Qatar Environment and Energy Research Institute. He works for the development of oil-water separation technology, which can be used for oil spill cleanup and produced water treatment. I think this is one of the important subjects that we need to focus on, especially at those days where, the oil spill is going to be a real threat to all the desalination plants in the Gulf. So hopefully Dr. Leo will give us his insight into this issue and tell us what is the best to do to prevent that. Please, Dr. Leo. I'll just put your presentation here, right? Okay. And this is forward, backwards.
Okay, thank you very much.
Thank you.
Thank you for the introduction. My name is Zhao Yang Liu. I'm a senior scientist from Qatar Environment and Energy Research Institute, Hamad bin Khalifa University. Today my presentation topic is about the oil spill management to prevent the catastrophic shutdown of a seawater desalination plant. So my presentation content will include the research background, QEERI research for oil-water separation technology, conclusion and recommendation. The research background, as we all know, Qatar and the GCC country are heavily rely on the seawater desalination to provide the fresh water with the purpose for drinking, industry, agriculture, and tourism. And Qatar and most of the GCC country only have a few days of strategic water storage in case of the emergency. There are 2 main desalination technology adopted by GCC country. One is the thermal distillation. Another is reverse osmosis membrane filtration. Between these 2 technologies, the thermal distillation is still the dominant one in the GCC country. On the other hand, GCC region is a global hub for the oil and gas exploration, production, and transportation. The intensive oil industry activity presents a severe risk which related to the oil spill. Oil spill can damage the marine ecosystem, contaminate the seawater. The oil spill could reach the seawater intake portal, which is located in the seabed, and transport through the pipeline and arrive the onshore seawater desalination plant. In the case of the thermal desalination plant, the heat exchanger efficiency will get reduced. The quality of the final water product will be compromised. In the case of the membrane-based desalination plant, the membrane surface will be filled by the oil, and the water flux will be reduced due to the membrane falling. In some severe case, the desalination plant has to be completely shut down to prevent the severe damage and the costly maintenance. In history, there are some record with the desalination plant shut down and the water supply disruption caused by the oil spill in GCC country. The affected country includes the United Arab Emirates, Saudi Arabia, Kuwait, Egypt, and Yemen. So there's many different causes for the oil spill, including the offshore oil drilling accident, the pipeline leakage, the oil tanker collision, illegal discharge from the ships, even the geopolitical conflict adding the risk with the oil infrastructure being attacked by the military. So during the oil spill, there's many different forms of oil coexisting in the seawater, including the free oil, dispersed oil, emulsified oil, dissolved oil, and oil wet solids. Due to the variety of the oil forms, the oil spill cleaning work is very complicated, especially for the emulsified oil. It is difficult to be removed from the seawater by using the conventional oil removal technology. So the typical oil spill response measures include two methods. One is a physical method. People will use the physical with a floating boom to contain the oil spill from spreading into the large area, followed by using the mechanical skimmer to collect the oil into the nearby vessels. The second method is the chemical method. People use the airplane or ships to spread the chemical dispersant on the surface of the floating oil to break down them into the small oil droplet. Visually make the oil disappear, but physically the oil still exists in the seawater. The using of the chemical dispersant sometimes may even further exacerbate the situation for the seawater intake for the desalination plant under the circumstance of the oil spills. As shown in the left-hand diagram, after the oil breaks down into small oil droplet, the oil becomes easier to be transported through the water body, reach the seabed. As we know, normally the seawater intake portal are located in the shallow water. And under the agitation of the wave and the tide, the oil droplet will be sucked into the seawater intake portal and transported to the desalination plant and contaminated the desalination equipment. So this green color diagram shows a very typical seawater pretreatment process is being used in the Qatar desalination plant. The pretreatment process chain starts with a physical screening, followed by the chemical coagulation, flocculation, media filtration. Anyway, the overall objective for the current seawater pretreatment in the desalination plant is to remove the solid particle and some organic substance. But until now, there's no any treatment unit in the process is originally designed for the removal of oil spill. So in Qatar, we do have the very stringent regulation. That is, when the oil content in the seawater reaches the threshold concentration, is 0.5 milligram per liter, the seawater desalination has to be shut down. So we don't want to see this severe scenario to be happen, because the shutdown of desalination plant will cause the water supply shortage, the economic loss, and even the social panic. To prevent such severe scenario happen in Qatar and the GCC, our research team in QEERI proposed a proactive measure has to be taken. That is, a comprehensive and a robust process with the adoption of advanced technology for the offshore oil cleanup, seawater intake, and onshore seawater pretreatment has to be installed in the desalination plant in Qatar and the GCC to prevent such catastrophic shutdown for the desalination plant in case of any oil spill incident. So we publish our research finding on the prestigious journal in the desalination field. So there's more technical details you can find in the published paper. So to contribute to this prevention of desalination plant shutdown caused by the oil spill, the research team in QEERI is conducting several research activities for the development of advanced oil water separation technology with the aim to efficiently remove the oil contaminant from seawater. The first research activity is the development of a new environment-friendly process for oil water separation. So in Qatar, and I think also the same case for GCC country, during the oil exploration, there's a large amount of oil contaminated produced water is generated from the process. The offshore produced water is being transferred to the small island called Halu Island for the treatment before any reinjection or disposal into the underground reservoir. So one of the key technology for the treatment is air flotation. But the problem is, to enhance the performance of air flotation process for the oil removal, the metal-based chemical coagulant, such as ferric chloride, has to be dosed in the process. This comes with some issues. For example, the treated water effluent will be stained into brown color due to the residue of the ferric ions in the water, and also the generation of the non-biodegradable sludge. So to reduce the environmental impact with this current industry process, our team in QEERI come up with a new idea to develop the new hybrid coagulant flocculant system with ferric chloride as coagulant and catechsin as a biodegradable flocculant. The new system comes with the advantage with a significant reduction for the usage of the metal-based coagulant, the ferric chloride, and the reduction for the non-degradable sludge for the process. The second research activity is turning medical waste material into the valuable product. So as we know, in Qatar, the healthcare sector generates a large quantity of fiber-based plastic medical waste, so such as the face mask, the apron, the bed sheets, which is being used on daily basis. So current practice to handle this medical waste is hospital designate some special waste treatment company to collect and dispose the medical waste into the landfill after the disinfection and incineration. So in our QEERI research team, so we develop a very simple and cost-effective approach to modify the medical waste surface to use as an efficient coalescence media. So during the coalescence process, the small oil droplet in the water will collide and aggregate on the fiber surface inside the medical waste. and the small oil droplet will grow up into the big oil droplet, a big oil drop. Based on the density difference, the oil and the water will naturally separate into two layers, get separated. This coalescence process is very environmental friendly process without any usage for the operation. So the third research activity is the development of inorganic nanofiber-based membrane for oil-water separation. As we know, the membrane filtration technology is known for its high quality for the treated water effluent, but there are still some issues for the commercial membrane. For example, one of the issues is low water flux for the membrane. As shown by the SEM image, the segregated pore structure is formed inside the membrane body, which causes very high resistance for the water permeation and lead to the low water flux. The second issue is the membrane fouling, because the majority of the commercial membrane is made by the polymeric materials, which mostly are hydrophobic and oleophilic, which lead to the oil fouling issues. So under this context, our research team come up with a new concept for the design and the developing of the membrane for the oil-water separation. There are two types. The concept is using the inorganic nanofiber to construct a membrane for oil-water separation. There are two types of membrane has been fabricated in our labs. The first type is called asymmetric membrane with inorganic nanofibers on the top of the membrane as a function layer, and with polymeric microfibers at the bottom of the membrane function as a mechanical supporter. The second type of membrane is called a symmetric membrane with a zinc oxide nanorod grow on the commercial carbon cloth. So both types of membrane has a common advantage. The first one is high water permeation flux attributed to the three-dimensional interconnected pore structure, which lead to very low resistance for the water permeation. The second advantage is low oil fouling tendency, because you know the intrinsic hydrophobic and oleophobic property from the inorganic materials. Anyway, we publish all the technical details, including the membrane fabrication performance test in a number of peer-reviewed journal papers. You can find the details from the publications. So we're also doing the prototyping for the water treatment technology in QEERI. So as shown in the diagram and the photos, our team developed a pilot scale prototype based on the working mechanism of coalescence I mentioned before. So coalescence is a very environmental friendly process with the advantage of chemical-free operation and the small footprint for the equipment, which can be used for the offshore platform, which face the space and the logistic restriction. So finally, the conclusion and the recommendation. The operation of desalination plant is very sensitive to the quality of feed water that is influenced by several factors, including the quality of raw seawater intake procedure, and onshore pretreatment methodology. The existing desalination plant must be re-evaluated and redesigned on the basis for all these factors for oil contaminant removal, and to guarantee the quality of feed water in the circumstance of oil spill. Since most of the oil spill happened by accident, and nobody can predict how badly, where, and when they will happen. Therefore, a proactive measure has to be taken, that is a robust oil spill management plan to prevent the desalination shutdown has to be installed in Qatar and the GCC country. That's all. Finally, I would like to thank the contribution from my co-author for the research, Dr. Ulo Shang, Dr. Radi, Dr. Jaya, Dr. Jenny Lola, and thanks the funding support from QEERI and HBQ. That's all for my presentation. Thank you for your attention. Oh, okay.
Thank you very much, Dr. Lee, for this informative presentation. We'll take a few questions before we go to the second paper. I'll take the privilege for the first question, please. I'm the chairman. Okay. No, Dr. Lee. Okay. Okay. No, just my question, Dr. Lee, do you think this, for a large oil spill, especially, when it happens sudden and it happens could be very vast spill, do you think that membrane, you were talking about smaller plant, you can't have big plant to treat the oil spill, especially with membranes.
Yeah.
I don't know, do you think that will be economical to be considered?
The chemical process?
Sorry?
You mean the chemical?
Yeah.
Okay. That's a good question. I have to admit, it's for large area oil spill, it's a very challenging task to be cleaned. And maybe it takes months, even years, to clean the oil spill in the marine environment. So like I recommended in the presentation, the oil spill management has come with a very comprehensive and integrated process. We include the offshore oil cleanup, the seawater intake procedure, and onshore desalination plant pretreatment. Especially, I like to recommend the current seawater desalination to install the advanced seabed water intake method. The sand on the seabed will function as a pre-filter to filter out the oil spilled, before enter into the onshore desalination plant. Yeah, yeah, it's a very challenging task. Yeah.
Thank you very much.
Microphone, I don't know. Muhammad Souf from Saudi Arabia. In Saudi Arabia, we experienced two large oil spills, 83 and 91, Nowruz and Kuwait. In 83, we stopped one plant, which is Al-Zubari. Jubail plant continued working. In 91, we maintained both plants operating with proper measures. It is always important to know where the oil spill is coming from. If it is short distance, it is a serious problem. If it is long distance, it's a very mild effect. Because with the long distance, the oil spill, from my refinery background, I could say that the oil will be divided into three components: very light, liquid, and solid.
Yeah.
The very light will evaporate mostly before the intake or even at the intake.
Yeah.
The liquid will come into the plant. It will affect the heat exchanger, but it will not affect the product because it will go with the vent system.
Yes.
Okay? So what we see, what we hear here in the Gulf is scaring people. Panic. Nothing else. One last comment. I am an advocate of beach wells, which is taking the product from under the water, from under the sand. And even I designed horizontal drilling of seabed intake. Thank you.
Thank you, Mohammed.
Thank you.
Anybody? One more question, because we are just behind you, Mohammed, please.
Hello, hi. Thank you for the nice presentation. This is Dr. Zainab from University of Bahrain. I have two questions. One regarding the natural coagulant. Have you tried in your research investigating some natural coagulant instead of the ferrite chloride for such application? Like readily available plants in the country could be used as natural coagulant for the same process. And my second question is regarding the face masks and the medical waste. These are really interesting topics, and we are basically solving two problems together, the waste and using it for some useful applications. So my question is, what sort of pre-processing procedure you use before applying that for your technique?
Yeah, thank you for the question. I will answer the first question. So as for the natural coagulant, in our research, we're using the very easy commercial available, catechin as our first exploration to test our concept. Of course, there's many different types of natural coagulant other than the catechin, even locally available. Even some researcher, adopt from the palm trees, extract from the seaweed. Yeah, this is some of the option to replace the catechin, use as a natural coagulant, folliculant. Yeah. For the second question regarding the procedure to modify the medical waste, in our team in QEERI, we're using industry-adopted technique called spray dry. We spray our, some polymers on the surface of the medical waste subject, generate a porous structure to enhance and increase surface area for the oil coalesced and grow up on the surface and achieve the efficient separation for the oil and the water. Yeah.
Thank you, Dr. Lee. Thank you very much for your presentation. Just please quickly, because we are running out of time.
Thank you. We have recently now, it's just keep repeating that one of the issues, it's running, yes?
Yeah.
Yes. Okay. The jellyfish, we have some issue on the jellyfish and let's see there, it's affecting the RO plants intake. You have presented that the chemicals on the first 2 or 3 slides. Can we use this kind of chemicals to manage this kind of effective?
So you mean the chemical dispersant?
Yes.
Yeah, that's also very good question, I may forgot to mention very good point, very important point. Currently, all the oil spill response measures are designed to put focus to prevent the marine environment damage rather than to prevent the onshore desalination plant shutdown. So the people only care about the marine environment protection. So that's the reason they're using the chemical dispersant to break down the oil flakes into the small oil droplet. Only rely on the natural environment to degrade it. But maybe this further exacerbated the situation. The breakdown small oil droplet will transport to the seabed and suck into the seawater in portal and transfer to the onshore desalination plant and contaminate the desalination plant equipment. So we need to put this into the consideration in the future design of desalination plant. Yeah. There's many historical records. Some countries like UAE, Kuwait get affected because of oil spill to disrupt the water supply. Yeah.
Thank you, Dr. Lee. Please, you can take your seat. Thank you very much for your informative presentation again. And I will leave the podium to my colleague, Engineer Hamid, to introduce the second lecturer.
Assalamu alaikum. Our second speaker is Dr. Wafa Rawahi. The topic of her presentation is use of activated carbon for seawater desalination by using solar power. The aim of her study is to enhance the desalination process and also minimizing the cost by utilizing the renewable energy, particularly the solar power. Welcome, Dr. Wafa. Dr. Wafa Rawahi is a PhD graduate of the University of Shuri, UK, and specialized in analytical and environmental chemistry. Dr. Wafa is a senior lecturer in applied chemistry section of Applied Science Department at the University of Technology and Applied Science, Oman, and is the head of that chemistry section. As a chemistry, her research interests in water research in relation to human health. She worked on the development of a vanadium specification using solid phase extraction method. In addition to this, she has experience in conducting some research related to heavy metals analysis and their removal using electrochloration method with the aid of solar energy. Recently, she is working on activated carbon applications in desalination and purification of drinking water and seawater. She is also conducting some project on Oman about medical plants, focusing on the elemental levels and their medical applications. Welcome, Dr. Wafa. The floor for you.
Thank you. Assalamu alaikum wa rahmatullah. I would like to thank you for this introduction, and I would like to thank the Gulf Water Conference for accepting this research paper. I will start with the topic. As you can see, it is the oxide-activated carbon for seawater desalination with the aid of solar energy. These are the main points of the presentation. As the speakers before me already introduced the main challenges in the Gulf countries and the scarcity of water in which nowadays all Gulf countries are towards desalination. So in Oman, it has started since the 70s, the first desalination plant in Al-Zubari. And then due to the increase consumption and the increase of the population, as well as the industrial and the tourism as well in tourism industry, there is an increase in the need for water. So due to this, there was an increase also in the number of desalination plants in Oman, now about 5 major desalination plants. And as we saw from the previous speakers, most of these desalination plants, they are using the reverse osmosis, so or the membranes. So, and as you know, there are lots of environmental impact on these membranes. So as researchers in the academic institutes, we are looking into different ways or different technologies in which we can implement or increase or solve such issues. As you know, nowadays activated carbon is one of the raw materials in which it has lots of focused on many researchers due to the sources. It can be available from different raw materials such as solids from agricultural plants or from different solid or sludges. The production of activated carbon is not that much difficult. So the two main process for production of activated carbon is the pyrolysis and the activation, either through chemical activation or physical activation. Depends on the application at the end of this activated carbon. Also, it has a large surface area and porosity, which give it the main property of the use in different applications, such as in the desalination or using it as filters in the water purification. Also, the regeneration of activated carbon using different ways, using thermal regeneration or electro regeneration, as well as bio regeneration. So from here, the aim of this project came to investigate the production of large amount of pure water or desalinating water with less energy consumption by environmentally friendly method using activated carbon prepared from agricultural waste. So the main objective of this project is the preparation of activated carbon using physiochemical process, and then the analysis and the characterization of the produced activated carbon, followed by the preparation of the oxide activated carbon, then the preparation of the oxide activated pellets, and then finally the application in the desalination process. So as I mentioned before, the preparation of the activated carbon, first of all, it was the collection of the agricultural waste, drying it, washing it, then drying it and converting it into powder, then the process of the pyrolysis using in a specific furnace, and then under the flow of nitrogen with the increase of the temperature at 10 degrees per minute. Then after the carbonization, it was the activation using 1:1 ratio of potassium hydroxide. This is the okay. Then it was dried. Then again it was put under the nitrogen flow, and it was like changed in between nitrogen and carbon dioxide at temperature of 700. After that, it was washed with HCl for neutralization and characterized by SEM and EDX as well as FTIR. The next step after the preparation of the activated carbon is the preparation of, or the oxidation of the activated carbon, where it is the most, here is the innovation took place using a Hammer's method. So the activated carbon was mixed with the nitrogen, so the nitrate, and it was oxidized by using potassium permanganate. After that, it was the peroxide was added, and then the activated carbon was, the oxide activated carbon gel was centrifuged and washed with HCl for neutralization. Then it was again dried and tested or characterized using SEM, and this is the process in which the oxidation process in the lab after the preparation. Here it was then the characterization. First of all, we have to make sure that we have the activated carbon and to make sure that the oxidation took place. As you can see here from the carbonyl groups, it's showing here the OH and the carbonyl group and CO, in which the surface area is here of the activated carbon is oxidized. This is the SEM comparing the activated carbon surface area with the oxide, in which we are checking the porosity and also the surface area and comparison between the two products. Also to check and to make sure that the oxidation took place, we also did the SEM, the EDX, in which you can see here in the comparison between them here the carbon level was almost 78.8. Here there is an increase in the oxidation where you have the oxide activated carbon. Also here there was a change in the surface area of the oxide activated carbon. The next process is how can we use this oxide activated carbon and how can we prepare it for the desalination. So we started with the powder, then we thought to make it into pellets. So this is the process in which we use cellulose triacetate with first of all the dissolve of malic acid with methanol, then the addition of dioxane, the cellulose triacetate, and the oxide activated carbon to then they were mixed together, then the formation of the pellets, and then the washing, and after that the uses of these pellets in the desalination. To start up, we started with the lab scale, in which we tried to test the oxide activated carbon using it as a powder, as a pellet, or a pellet, using the same masses to check the efficiency. Is there any effect on their efficiency in the desalination? So and also to test what will be the temperature required for desalination if we use any of these products. So we tried to do 3 trials, one without using the activated carbon, only the seawater, the other ones, one with the powder and the other one with the pellets. So we observed that the seawater with oxide activated carbon, the boiling point was around 40 plus or minus 4, while almost 100 as known without these pellets or without the powder. Also, there was a change in the flow rate or the production, the amount of produced water with the oxide activated carbon was almost double. So then we tried to test it using the solar panel, because this is our aim, to use the solar energy in the desalination process. To come up with this, we made a setup, we designed the setup in which we have 2 tanks, one for the seawater, the other one for the collection. It is designed with outlet and inlet. Also, we added the batteries, and here we have a coil of 12 voltage, and we have the main tank and the water pump with a sensor, in which it controls the temperature. So when the temperature is more than 50, it will stop heating. When it came to 40, it will heat again. So this is the actual design in which here we try to do the desalination in this setup. And here you can see the full setup. And as you can see here, we put the oxide activated carbon in the first tank. And here in this one, it is showing that the boiling point around 39 degrees for the water. We tried to compare the amount of required energy and the amount of time required using the oxide with and without the oxide activated carbon. As you can see from the graphs, almost we need half the time for collecting the same amount of water as well half of the energy. So we try to, we are trying here to prove that with the use of this product, almost half energy is required. After that, we sent the water we tested the water. We did the elemental analysis for both major and trace metals. Most of the trace metals, it is below detection limits. This is why I didn't put it here. The major elements, as you can see here, after desalination, it is within the WHO with the use of oxide activated carbon, and also within the water quality standard, drinking water standard for Oman as well. To conclude with, the aim of this project was achieved by by producing a product which is economically friendly and it costs less energy. The activation was by the use of potassium hydroxide and physiochemical activation. Based on the EDX and ES, the oxidization was around 37% of the activated carbon. The boiling point of water was around 40 plus or minus 4 with the use of the oxide activated carbon. And the quality of water was within the acceptable standards of WHO. We already published, we used the same product also for checking other application as purification of water. We use it as a filter for removal of chromium-6, as well as we tried the same product for as a membrane instead. We are now working to use it as a membrane to get larger surface area. And also we are trying to use it as a catalyst for other products. So this is not the latest version, by the way. As a future plan, we are targeting. We already got the patent for this product, and now we are trying to produce the product, seeking investors, and also trying to make small desalination plant in which we can compete with others, and we prove that this method as a product can compete with others, especially during emergency or during in far or and some areas where desalination plant cannot be there. I would like to thank my team members of this research. As well, I would like to thank Ministry of Higher Education, Sultan Qaboos University, DM, and definitely Nizwa University and the University of Technology and Applied Sciences for their support and funds during this research. Thank you.
Thank you very much, Dr. Wafa, for your interesting presentation and very valuable topics that might be introduction to a new technology. Due to the time limitation, maybe we can allow 3 questions, but anybody interested in this topic can have a side discussion with Dr. Wafa after that. Yes, please welcome your question.
Hamad Soufi, Saudi Arabia. Thank you. It's an excellent work. One question: cost. Did you do any cost analysis?
Yes.
Do you have any results in that?
We did only small cost analysis for the required, for the amount or the benefits that will be and the cost for, especially the raw material it's not costly, only the cost will be on the preparation and the activation. The other part is the desalination plant. However, regarding the energy, it is solar energy, so it is, and even the setup is very cheap one. So we did roughly the cost based on small units.
And availability of feed, agriculture.
Yes.
We don't have much agriculture in the Gulf.
Yeah.
Where are you getting your feed?
Yes.
What is your source?
It can be used, as I said, it can be used in some of the agricultural places where salinity is a big challenge, especially in Oman, in Al-Batina. Also, it can be implemented in some areas like in the mountains and where it is very difficult to have a big desalination plants.
Shukran. I think this technology can help to desalinate brackish water mainly, especially because in many areas, remote areas where there is no energy, sea, but there is brackish water, it can be helped. Okay, we can go to the second question. Any question? Yes, please.
Thank you for the presentation. It's very interesting technology for the seawater desalination or breakage desalination. My questions, during your test for the water desalination, have you observed any salt accumulated on the surface of the carbon materials?
You mean the pellets themselves?
The salt.
The salt, there is, the salt will be...
white color salt accumulate on the surface of the black color carbon materials?
Yes, we tried to try different. There will be some salts definitely because this is activated carbon and it has higher porosity. However, with the use of the membrane and this one, we tried to test these pellets for 5 trials. And the amount of water produced was almost the same. So also, we worked on the regeneration. You can, because there are 2 tanks. See, most of the saline or the salts will be in the tank at the low. These pellets, they will come on the top. So most of the salt will go low, but there will be some salts within these activated carbon pellets that after some time, they need to be regenerated.
Another question? Yes, please. Yes, go ahead.
Thank you, Dr. for excellent presentation. I'm just following to the first questions. At the end, total cost, producing 1 liter of water, in your technique, you are saving time and energy, but you're adding extra cost for the producing of the activated carbon and using the materials. But at the end, is it going to save more money or less money or almost compensating?
The cost will come at the beginning because definitely when you start your project, you will need your labs or your furnace for the production. Later on, the cost will be almost higher per month. So the cost, it will be on the production of the activated carbon. You might need a big furnace. Then these for the chemicals. And as you saw, the chemicals are very cheap ones. They are not really expensive chemicals. The process, somehow, it is a bit long for the oxide activated carbon, but what you need to use only very small amount. Per pellet, we calculated 0.1 gram. So the amount that is used for the during the desalination is very small amounts. And as well, you can regenerate these pellets.
Okay, we can give you one chance. You can ask, please.
First, thank you very much for the interesting presentation. One question, when we talk about activated carbon, you know, have you analyzed the form of activated carbon, the effect, whether it is a granular activated carbon or powdered activated carbon, and how would that affect the process and the efficiency?
Yeah, thank you. Actually, we tried only with the powder. So after preparation of the activated carbon, we convert it into a powder and we sieved it into 100 microns, so we have the same surface area. So we are towards the powder itself. So the smaller the particles, the more the surface area, and easy to oxidize it. So you can have the groups, the functional groups of the hydroxide, the ketones, and the carboxylic group on the surface. So whenever you have smaller size or smaller surface area, it will be better compared to granules.
Okay, thank you very much, Dr. Wafa, and wish you all the best on your career and your researches. And we will shift to the third speaker. My colleague Ali will introduce him.
Well, we are coming to the last presentation. And this presentation will be delivered by Dr. Mansour Ahmed. I think by now you know him very well. He's delivering this paper on behalf of his colleague, Dr. Hassan Abdurrahim, who couldn't make it to come to the conference, and he asks the co-author, Dr. Mansour, to present it. No. He's well known, so just quick introduction, please, Doctor. A very quick one. Dr. Mansour is a research scientist and program manager of water desalination technologies at the Water Research Center in Qatar. His areas of specialization is freezing desalination, forward osmosis, I hope. And he will be talking about forward osmosis this time, right? Okay. And other subjects he's been working on was on brine concentration, salt and mineral extractions. So the floor is yours, Dr. Hassan. دكتور حسن قلت انا
انت دكتور منصور 2 1 ان شاء الله بس اعتقد هذه It's okay, doesn't matter. Oops. Okay. Bismillah ar-Rahman ar-Rahim. Once again, this is Dr. Mansour Ahmed from Qatar. Today, in the early morning, I provided a presentation on innovative desalination technology with different types of the technology when used. I'm going today a bit elaborate in one of the patented technology, which is based on innovative approach for desalination and cooling using forward osmosis and thermal recovery and vapor absorption cycle. This is based on a patent which was achieved by Dr. Hassan, and it's basically, we are, as I mentioned earlier, that we are looking and seeking for the opportunity to own the IP based on establishment of new technologies and advanced technologies targeting seawater and brackish water desalination, as well as zero liquid discharge. And we are looking at the ability and the possibility of establishment of a private and enhanced private sector in Kuwait in order to take a lead in commercialization of these technologies, and also to improve and also enhance the national manpower to handle and deal with this type of technologies. This is the agenda of today's presentation, and I believe similar to Kuwait and other GCC countries, we suffer from water scarcity and hot weather conditions, which are both predominant problems facing Kuwait and other GCC countries. Now, with the case of water scarcity, I believe we resolve these issues by having different type of seawater desalination, and with the case of hot weather, that will mitigated by using heating and air conditioning systems in almost every building in Kuwait. The desalination plants in Kuwait consume 460 terajoule of energy, which represent 54% of national fuel consumption. Air conditioning, on the other hand, systems in Kuwait consumes about 60% of the total electricity demand in Kuwait. Other literature shows even more than this percentage. Both desalination and air conditioning systems are very intensive and energy-intensive technologies. Unfortunately, in Kuwait, we burn crude oil, natural gas, to secure the operation of the power plant needed for desalination and air conditioning systems. Therefore, there is substantial needs for the development of the integration, desalination, and air conditioning system to be implemented some way, somehow. But once we look at this scope, this is required. For example, with a case of air conditioning system, we should also consider the district cooling systems, and especially for the new development, that when the government will build the houses, so it has to be linked with those technologies. Besides, we are not looking at very, let's say, large-scale application, but also we are looking at small-scale application to confront the challenges of water demands in remote area as well as the emergency. Therefore, we introduced a technology is based on integration of forward osmosis with the absorption cycles. We had the patent already, and basically the patent composed of vapor compression, or let's say vapor absorption cycle, which is based on a single effect using lithium bromide chiller operated by a low-grade thermal energy. It does not require the mechanical compressor, as it was replaced by an absorber, pump, and generator. And we use the distilled water as refrigerant, which is an eco-friendly refrigerant. As for the forward osmosis system, we are using the integration of forward osmosis with thermal separation system. The advantage of using this type of technique, it can be run 24/7 without need of link the system with the grid. Not similar case with the RO, because RO is run with the PV, but here we need is just thermal process, so that can be managed. This is a bit, let's say, a bit complicated, let's say, schematic diagram that shows the integration of forward osmosis with the absorption cycle. From this slide, as you can see, the forward osmosis, basically, we feed the seawater, and the other streams of the draw solution with the polymeric solution is fed in the other side of the forward osmosis modules, so that draw solution will be diluted, and after extracting water molecules from seawater, and it requires heat. So that heat has been generated by the condenser. So with the case of the absorption cycles, we pump the absorber into the generator, and basically once we have a heat comes from the source of motive steams, the vapor goes into the condenser, which heat up the draw solution of the forward osmosis stage. And this is a technique that we are basically exchanging the heat. We heat up the draw solution, and at the same time we are cooling. We have a coolant that can be utilized for district cooling system to chill the city or the surrounding buildings. Now, forward osmosis technology, why we chose forward osmosis technology? So now, the driving force of forward osmosis is relying mainly on the osmotic difference between two streams. Seawater from one hand, other hand is the draw solution that is man-made chemical solution that we prepared with high osmotic pressure in order to have the capability to extract water molecules from the seawater penetrated through semi-permeable membrane. It has a number of applications, as I mentioned earlier, including seawater desalination. Now, forward osmosis as standalone, as I mentioned earlier, cannot be implemented as a standalone process. It's required subsequent system in order to to produce the fresh water, and at the same time concentrating the draw solution and recycle it into the forward osmosis module. According to the literature, this table shows the comparison between the conventional thermal desalination technologies and forward osmosis process on low-grade heat utilization. In this study, basically, they compare forward osmosis based on mathematical modeling with MED and MSF, and the results showed that forward osmosis can produce 3 times higher than MSF, 2 times higher than MED. This is another literature shows that which shows the graph, which comes from one of the literature, is based on energy consumption by different desalination technology. They compare forward osmosis with MED and MSF and RO, and they found forward osmosis is the lowest in terms of power consumption, and it was estimated in this study 0.8 kilowatt hour per cubic meter. Now, comparing reverse osmosis to forward osmosis. Again, this is from the literatures. It shows that the water recovery with the case of forward osmosis can go up to 75%. So far, we achieved at KAHRAMAA 55, and we received with the case of forward osmosis integrated with RO 60%. So experimentally based on pilot plant proven at KAHRAMAA, we achieved 60%. But according to the literatures, can go up to 70. And there is high potential. Again, it's about nanofiltration, which is the key that enable any desalination system to increase the water recovery as long as you have high water recovery NF integrated with any desalination system that has the capability to produce higher water recoveries, such as in forward osmosis. Forward osmosis doesn't need high pressure pump, as in RO. The fouling and scaling rate is much less compared to reverse osmosis. Therefore, also, there is an absence of plastic materials, and also the chemical pretreatment is different, I mean, in terms of intensive chemical additives that they put for RO. Forward osmosis doesn't require that, but it needs to be optimized. For example, SDI, with the case of the SDI, RFO can go up to 11 based on Tiobo data sheet. At KAHRAMAA, we investigated and developed forward osmosis at different level, starting from theoretical, moving toward the laboratory scale, then semi-pilot plant, and later we completed even several projects on pilot plant level, and currently we are in the phase of demonstration plant. And the ultimate goal is the integration of forward osmosis technology with renewable and waste heat in order to minimize and in order to run the technology as a green technology. Based on international collaboration. So KAHRAMAA had a collaboration with one of well-known company in Japan. They deliver their own full-scale or commercial-scale forward osmosis membranes. Whereas the forward osmosis process, we made a collaboration with one of well-known company in the United States in order to deliver their pilot plant, and we designed it together. And once we received the pilot plant at the beginning, it was not working properly, so we put our efforts in order to develop the process, and we succeeded on that by changing certain component in the system, and we were able to successfully running forward osmosis based on integration with thermal separation process using Colisar. Now, it's very important to point out that, for example, the American company doesn't know any details about the membrane that we use from Japan, and vice versa. The Japanese they don't have any idea how the process works, as we signed NDA. So the advantage of this project, KAHRAMAA, this has the full information from both sides. That technology actually helped us and lead us to scale up the process. We investigated a system with 50 cubic meter per day forward osmosis, and this is the image of the pilot plant, which we use full scale, commercial scale membrane delivered from Japanese. And the overall result that we achieved from the experimental works, the total energy consumption, for example, with the case of forward osmosis, 1.4 kilowatt hour per cubic meter. This is for the system that we use, and this is without electrical heater. And we scaled up based on the techno-economic studies. We showed actually that this technology is feasible up to 1 million gallons per day. And the system was able to produce a let's say drinking water quality as the product reached 100 ppm with a salt rejection of 99.8% at water recovery 50%. This is just the table shows the major physiochemical analysis of water samples for the feed and the product water. Now, the desalination part, it was covered by experimental works. Now, with the case of the absorption cycle, we conducted the experiment through mathematical modeling. These are the software packages being used, process simulation environment, and the engineering equation solver. Basically, the process simulation environment is covering the calculation of mass, heat and mass transfer and balances, and predicted design and off-design performance, monitor and optimize the plant performance, and plan modification and upgrades the existing plants. As for the ES, is general equation solving to solve the linear equation and differential equation, and also provide high accuracy thermodynamics and transport the properties of hundreds of substances. This is the formulas that have been used in the evaporator simulations, and these are the heat and mass balances that were used and considered in the absorber simulation. And this is also the heat and mass balances that were considered for generator simulation. These are the quick results. I go directly to the result that is already available in the screen. As you can see, the design of the forward osmosis, it was designed with a capacity of 1,300 cubic meter per day, and the specific energy consumption is 0.5 kilowatt hour per cubic meter. This is from the desalination side. But from the absorption side, we need thermal energy, which is based on the mathematical modeling, shows that 2,500 kilowatt. And the draw solution recovery system requires 1,900 kilowatt in this case. And at the same time, we can generate the cooling load, which is 5 tons of refrigerant that can be utilized for a district cooling system. In conclusion, for this type of technology, as I mentioned earlier, currently we are in the design phase because we have a proposal in order to implement the full scale based on actual physical pilot plants integrated to each other in order to show the technology running. And our target is to implement this technology with 100 cubic meter per day, and is currently under designing phase, and hopefully that this technology will be running within this year. And we are, as I mentioned earlier, in this type of technology, it solves 2 challenges: water scarcity and also the air conditioning system that is needed. We believe it has high potential to be implemented in farms or remote areas, as well as even the emergency situations that can be implemented. And the most importantly is we are trying to commercialize our own technology. We want to own the technology. We want to put our own control on those new IPs with the aim of establishing companies through private sectors. Thank you very much.
Thank you very much, Dr. Mansour, for this informative presentation, and congratulations for the patent. I would like to open the floor for discussions, please. Dr. Khalid. Dr.
Go ahead. Thank you, Doctor. This is very interesting work. I can see that you're running at a very high silt index, silt density index.
Yes.
Well, I think forward osmosis needs to be piloted in this part of the world because it will definitely open the door for low-cost desalination technologies. But running at 11 SDI, would the membrane manufacturer guarantee this value? I mean, as opposed to the conventional reverse osmosis membranes that maybe maximum you can get 4. So would they guarantee it? This is the first question. And the second part is that you're running at a very high recoveries of 50, and I see a figure of 75. So what would the time that is required for you to do cleaning, membrane cleaning?
Yeah.
What would be the cleaning cycle? Thank you.
Regarding the first question, now, according to the data sheet, even I can mention the name of the company, which is Tiobo. Based on international collaboration with Tiobo, we investigated this technique so far with open seawater and also beach well. But beach well, as you know, it's very fresh water, it's very pure, so it's not similar case with the open seawater. Our target, actually, we have, unfortunately, one desalination plant which is located up north of Kuwait, which is suffer from high silt and sand. And the problem is that turbidity in certain occasions reach 800 NTU. And they have to shut down the plant. Unfortunately, the reason behind establishment of this desalination plant is political decision rather than technical. But they still running the desalination plant. MSF is suffer a lot from scaling and fouling. So maybe today morning I highlighted several FO systems. So for example, maybe some of you could ask why I use FO, RO, because logically I'm going to use RO, I mean cheaper in terms of OPEX and CAPEX. So the reason is we are developing FO to confront the challenges in Sabia site. So FO has the capability to handle high, let's say, a bit high turbidity. In fact, if you look at the oil industries, they are using very, very high turbidity water with forward osmosis. And it's reached already commercial application, not in a small scale application. It succeeded with their industries. But in terms of desalination, because now we need to look at the performance once we implement this technology in Sabia site. Forward osmosis doesn't mean that it will not foul. This is not true. But fouling rate is much less compared to the RO, because in RO they are using hydraulic pressure, whereas in forward osmosis they are using osmotic pressure difference between two streams. This is number one. And regarding your other point, you mentioned that water, how we can reach 75% or 70 or so. Again, I mentioned in earlier my presentation, and I said that nanofiltration is actually going to play the main role to reach that level. Because imagine that if you deal with a sodium chloride solution, you will have no issues of scaling. So this is the idea. But the question is how I could increase the water recovery of nanofiltration. Because nowadays, so far, it's reached 80%. It's proven in Saudi Arabia. And so far in Kuwait, and also I heard the SWIC or maybe reached same level, which is 90% water recovery, but it's still under R&D. We run an F pilot plant, and we reached 90% water recovery. But sulfate is dictating what is the water recovery of the NF. So still we face a problem. There is other technique, but maybe later stage that we can talk about other technology like liquid extraction, like EDM technique that can help to manage or to reduce the sulfate in order to increase the water recovery in the nanofiltration system?
Dr. Mohammed?
Shukran, Dr. Mansour. I think we'll continue discussion. I'm a lover of nano. We have the nano. We started the nano actually in Saudi Arabia back in the 90s. 90%, yes, we reached. Actually, the 90% which we reached was based on laboratory distillation of seawater. We distilled seawater to see what is the point of turbidity appearance and what is the point of scale formation. It was 91 turbidity and 94% recovery for following salt, which is mainly the calcium, sodium carbonate. This was with a nano product, okay? So nano is a key issue, understand? My question and suggestion is this, cost analysis. I come back to the cost. Do the cost analysis, and maybe next conference or before, we see that, the result of the cost analysis, and also putting the nano inside the system and using solar energy. Thank you.
Sure. Thank you. Thank you very much for your comment.
Well, any more questions? I think we are coming to the end of the session. Thank you very much for attending here with us. And thank you again for all the presenters, Dr. Mansour, Dr. Wafa, and Dr. Leo. We'll see you again, inshallah, for the other sessions, coming sessions. Thank you very much. See you then. Bye-bye.